Welcome back to Wood Engineering. I'm Jeff Barojko from Carleton University, and in this video, we're going to continue our discussion of beam design by talking about shear resistance for lumber. And since lumber and glulam shear design are significantly different, we're going to cover these in two different videos. So the first one here is going to cover shear resistance just for lumber, and the second one will cover glulam. So first, before we go into the standard design equations, let's just recall what exactly is happening when we are looking at shear stress in a beam, and we want to limit the shear stress in our beam to be less than the limiting shear stress. So if we have a rectangular beam like the one shown here, and I look at the shear stress in the beam, you'll recall that the shear stress distribution in a rectangular beam like this should be parabolic. And if I want to find out what this FV is, so if FV is my shear stress, then you'll recall the equation for FV from previous mechanics course, which looks just like this. VQ divided by IB, where V is the shear force at that section, I is the second moment of area, or the moment of inertia, which we're usually pretty familiar with. B is the base, like the width of the cross-section, and Q is the first moment of area, which looks something like this. So if you recall the first moment of area, this is how we calculate the first moment of area at the center of the section. So Q changes depending on which part of the cross-section we are with respect to height. What we do is we take the area to one side of the neutral axis, and we multiply it by a lever arm, which is the distance from the neutral axis to the center of the area. So if I'm looking at the center of the beam, where FV max is, which I'm identifying up here as FV max, then I basically take the area of the top half of the beam and I multiply it by the distance d over 4, which is the distance between the neutral axis and the centroid. So if I want to calculate what is my Q center, just to reiterate, which is the same location, I have A prime, which is the area, just times d divided by 4. A is B times d over 2, and d over 4 here. So what we end up getting is BD squared over 8 for the center of the section. And this applies only to rectangles, obviously. I forgot to indicate here that this is shear stress that we're plotting. Okay, so now if I want to sub everything in to find my FV, what is the actual shear stress at the center of the cross-section where it's maximum, the peak of that parabola, then I'm going to sub into that FV equation. So I'm saying FV at the center is my shear force times my Q, which we just calculated, divided by my I, which is BD cubed over 12 for a rectangle, times B, and if I sub all that in, then I get 3 over 2 times V divided by BD, which is the same as saying 3 over 2 times V divided by A, which is the cross-sectional area. So what is V divided by A? Well, V divided by A is basically, if I wanted to say what would be the average shear stress over the height of the cross-section, like if I just considered that the stress was constant, which it obviously is not, but if I drew something like this, this would be my FV average shear stress over the height of my cross-section, we would find that the maximum shear stress is 3/2, so 50% more than the FV average. So that's what this kind of factor of 3 over 2 represents. So the peak is 50% greater than the average shear stress if I were to define average shear stress as V divided by A. Okay, so this F center is also my F max. So if I say FV max is for a rectangle, my FV center, which is the stress at the center height, we have 3 over 2 times V over A. Now, if I rearrange this so that I equated this to resistance, so let's say that I have an FV, which is a strength. So I say I have a certain shear strength of X MPa. And then I can set my V to be my resistance because I'm trying to rearrange to find an equation for resistance in terms of force units. And my A, if I set that to my AN, which is my net section, then I rearrange, then I get... So when I rearrange, I get VR, my strength in terms of shear. So my shear strength would be 2/3 of my FV times my AN, where my FV is my shear strength in terms of stress, my shear stress, and AN is the area of the cross section. So we can expect that our shear strength equation from the code may potentially look something like this. And indeed, this is what I get. So I'm talking here about longitudinal shear resistance for lumber. And the reason in lumber we call that a longitudinal shear resistance is because the failure mode for shear, for this type of shear in lumber, is longitudinal sliding of the straws. If my straws represent my wood fibers, is longitudinal sliding of the fibers relative to each other, which means breaking the lignin bond that is holding them together and shearing one set of fibers relative to an adjacent set of fibers. So that's why we call that longitudinal shear strength for lumber. And you can see that indeed the longitudinal shear strength equation VR is phi, which is a material reduction factor, FV, which is my shear strength in MPa, times an A, which is my area, my net area. And you can see that that factor of 2/3 is built right into the equation, which comes straight out of mechanics. And then the last parameter there, KZV, is just a size effect factor, which we get from the table, and we're used to doing that probably by now. So just to fill out the rest of these. Okay, so phi for this equation is 0.9. Capital FV is our lowercase fv multiplied by all of the modification factors, KD, KH, KSV, KT, which we get from our regular, we get our FV from our regular tables, and we get our other factors also from the regular tables that we're used to getting them from. AN is our net cross-sectional area, which we have already looked at calculating when talking about tension resistance. And KZV is size effect factor, which comes from this table, which we have also seen before on the left side here. It's the same as the one that we use for bending. Okay, so there's one other thing that we need to consider here, which is related to when we discussed compression perpendicular strength. When we said that for compression perpendicular strength, we had two cases, one for loads applied near a support and one for loads, which will be called effective all applied loads. And for loads near a support, you'll recall that we considered those separately because in that location, which we defined as being within D of the support, where D is the depth of the member, for that location near the end of the, near the support condition, all the force from the top of the beam, say, was transferred through the beam directly in compression perpendicular, and that there was not any significant shear in that region. And that's why we had to treat it separately, because for compression perpendicular, when we had the stress going all the way through the section, we had a larger deflection resulting. So now that we're talking about shear, we have basically the flip side of that, which is that in those regions near the support, we don't have any significant shear going through the beam, and therefore we don't have to consider the shear in that location. And we're going to clarify with a drawing. Okay, so if we're just looking at a simply supported beam like the one that I've drawn here, timber beam, and let's say I have a uniform load on it, it could be, we could be talking about any load here, but so we're just talking about a uniform load for now, just for this example. And I've drawn the shear diagram below it. And we should be very familiar with this shear diagram and how to draw it already. Okay, so in the regions that are within D, so I'm going to put a identifier here for where we are within D approximately of the support on either side. Just eyeballing this, but it's more or less correct. So now we have these zones that are within D of the support. And we'll recall that when we were talking about compression stresses being distributed, that right over in the area of the support over here, the stresses are directly going through the member from the top to the bottom, and they're basically direct from top to bottom. So that means that there's no turning of those forces. There's going to be no significant shear. Whereas as we get towards the center of the member, those loads have to be, the principal compressive stress has to kind of turn and go from being vertical to going on a diagonal before they go back to being vertical again at the location of the support. So that's what's happening within D. So the approximation that we're making is that within D, that's the area where basically those stresses, the shear stresses, are not significant, caused by the shear force. And that D is measured from the center of the support. Okay, as I've drawn here. All right, so if those shear stresses are not important, those shear stresses that are caused by the shear force in that region are not important, then instead of considering the shear at this point, which we know is WL/2, I'm going to consider instead that the applied shear to my beam is this point here, which I'm going to call VF star. So we will design for this. Okay, and same thing on the other side. At that location, we're going to have VF star. And it might not necessarily be as clean as this, because this is just a linear shear force distribution, but I think you get the idea. So whatever is the shear at that point, or the shear could be higher in between those points too. It depends on obviously the load distribution and everything. But basically the area here, we're going to ignore the shear force here. Okay. So, I mean, most often the VF star that we're going to use is going to be the one right at D, but that's not necessarily the case. Depends on the distribution of shear within the beam itself. Okay, so that's because in that region, are going to be transferred directly in compression perpendicular to grain. So that's what we're allowed to do for this particular longitudinal shear strength calculation. This does not always apply for every case, and as we'll see, we're not permitted to do that when we're calculating fracture, not shear, which we're going to talk about in a second. But for this one, for lumber beams within D of the support, we can basically ignore the shear forces within D of the support for the purposes of comparing to the shear resistance that we calculate using that equation. Okay, so that's not the only type of shear force in timber that we need to worry about. We also need to worry about something called the fracture shear resistance. Okay, so this is what notch shear resistance is all about. So we call it notch shear or fracture shear resistance at a notch. And I'm going to use my straws again to kind of show what I'm talking about in terms of notch shear resistance. I'm going to go to close up for this. Okay, so let's say that I have my beam like this, and I have all of my straws representing my fibers in the beam. And let's say that I have a notch So I'm just going to shift some of these fibers over to represent as if there's a notch here. Okay. So now I have a notch. Okay, so some of the fibers have kind of pushed out of the way. And this elastic band, again, represents the lignin that is holding all the fibers together. Okay, so now let's say that I apply a shear here. See if I can make this notch a bit more extreme, so it's easier to show. Okay, so here's my notch. So now let's say I push here. You know, I have shear being applied down here, just like in my drawing. So there's my drawing that I'm looking at. So I have shear applied to the beam, and I have a support at the notch location. So now if I am going to push on this, you can see what happens is that I am basically wanting to separate at that notch location and cause a fracture at that location. Okay, and so I am basically having a stress concentration at this. This is what's called the re-entrant corner. It's the corner where the notch comes down. And at that re-entrant corner, I get a stress concentration, and that stress concentration could form a crack, especially if I have a bad notch geometry. And we're going to talk about what's good notch geometry and what's bad notch geometry. And so I need a way to calculate this condition. This is obviously much worse than if I load here, because here I'm engaging the entire cross section. Here I could get a crack, and that crack can propagate through the entire member. So again, I can have a crack forming here due to a stress concentration at that corner. And I forgot the moment that's at that section. So there's obviously a moment at that cut as well. Okay, so one thing that I want to do to avoid this problem is to design notches with a better geometry if I can. And this actually does not come in. The geometry, this kind of geometry doesn't come into the equations, and they end up being very similar. Actually, the strengths for both of these geometries are going to be identical, but it's still a case of good detailing versus poorer detailing. So notch geometry. Okay, so here I have two different notches. These notches are otherwise functionally identical. The strength in the calculation will be identical, but one is considered a good notch geometry. You know, one is an okay notch geometry. The other one is a better notch geometry. Okay, and here I've identified the location of what we call the re-entrant corner. So it's the corner, it's an interior corner where the notch, it's basically the first corner that you run into from the support. Okay, so that's the re-entrant corner. It's the interior corner of the notch. So this is like an exterior corner, right? So it's kind of the interior corner part where the cutaway is. And that is where we're expecting to have that stress concentration. So that stress concentration is going to be worse if I have a sharper corner than if I have a more sloped corner. And that's why the geometry on the right is considered to be better than the geometry on the left. And we need to define some parameters here that we're going to use in our equations. This is the center of the support. That's where we're going to measure from. And we have two different depths that we are concerned with. One of those is the total depth D. The other one is what's called the notch depth dn. So it's just basically the size of the notch. And just like when we did calculations for AN, our net area, the notch depth is limited to, at maximum, 25% of the total depth. Okay, so that's a limiter. Over here, we also have a notch depth in the better detail. Same restriction of 25%. And the last one that we need is this parameter here, which is E, which is our notch length. And that is measured for this equation from the center of the support to the first reentrant corner. And this is where it will be on the other side. Now, if you're looking for, what is a good slope here, there is a suggested slope for this type of detail, and that slope would be 1 to 15. Okay, so now we have our E, which we're going to need in our equations. The larger the E, the worse the case is, and we have our notch depth dn, which also the larger the notch, the greater the reduction in strength. There's one more case that we should look at, which is what happens if our notch is on an angle. And what happens basically is we consider our E and our D to be parallel with the main axis of the wood. And that is going to look something like this. Okay, so let's say that I have a member that is at an angle and it's sitting on some support, and there's a notch cut out of the piece of wood so that it can sit directly on the support. So this might be a common case at the end of a rafter or something like that. Then how do I measure my dn and my E? Well, my dn is going to be the depth of the notch perpendicular to the longitudinal axis of the piece of wood. And the E is going to be from the center of the support to the reentrant corner again in the direction parallel, oops, that's going to be E, parallel with the piece of wood. I could probably draw that a little bit better to make sure that those lines appear more perpendicular. And you'll find drawings of this as well in the standard. So these dimensions are aligned with the member axis. Okay, so now how do we calculate our actual notch shear strength? So we have a different equation. So this is the equation for fracture shear at a tension side notch for lumber. And basically it's a very simple looking equation, except everything is built into that parameter Kn, which is the notch factor. So we still have our strength, we still have our modification factor phi, our strength reduction factor phi. We have our FF, which is our notch shear strength, which we'll talk about in a second. And we have our gross area, and then we have our Kn. And we're using our gross area instead of our net area here because all of the geometry of the notch cutout and the reduction of area caused by that cutout is going to be accounted for within Kn. I'm just going to finish this out, the parameters. Okay, so in this case, the notch shear strength, the fracture shear strength, FF, is given as a constant, and that is independent of the type of wood. And you'll notice that it is very, very small. 0.5 MPa is very small strength compared to the other strengths that we have in those tables, 6.3.1. So that means you get a big penalty for putting a notch because the strength is very low for notch shear. So if you can avoid a notch, it would be best to avoid a notch. Gross cross-section area, AG, doesn't account for the cutout, as I just mentioned, which is going to be accounted for by Kn. Now, Kn is where all of the magic happens for notch shear, and the equation is quite complex. So I'm going to write it out and provide all of the parameters. Okay, so this is quite a complex equation. There is D in there, which is our depth. There is alpha, which is a parameter we're going to have to define. And there is that one that looks like a funny N, which is eta, which we're also going to define. Okay, so a lot to unpack here. All of these parameters are provided in millimeters. And so you can tell this is kind of a curve fit kind of equation. We have our depth, our total depth, our notch depth, and E, our notch length, which we just talked about the geometry of E in these. So this defines how we pick E from the center of the support to the reentrant notch, the reentrant corner of the notch. Then we have these parameters alpha and eta, which are basically just to simplify basically the look of the equation above. And alpha is 1 minus basically the percentage of the cross section that is the notch. So it's dn over d, the notch depth divided by the total depth. And eta is E divided by D, the notch length divided by the total depth. So how long is the notch relative to the depth of the beam? And when I take all of these and sub them all in, then I'm going to get Kn, and Kn is going to be something less than 1, probably to reduce the strength of the notch. So I can do this big equation to do that, or I can also use a table, which I find in the standard. This is the number of the table in 08614. And this table gives me values of Kn square root D for a given alpha and eta. So I would calculate alpha, basically how deep is my notch relative to the depth of the member, and eta, which is the length of my notch relative to the depth of the member. And I have split this into two, but in your copy of the standard, it's probably on one page. In 08619, it's split into 2 pages. And basically, based on those geometry parameters, you'll notice that alpha caps off at 75% because we can't take up more than 25% in the notch. I can pick the value, of Kn square root of D. Then if I want to find Kn, what do I have to do? I basically have to divide this value, whatever I get in the table, I divide it by the square root of D. And then I'm going to get my my actual value of Kn. And that's easy enough. And I can interpolate these values. If I don't have exactly the number here, I can interpolate in between these values to get a value for me to use in the equation. Okay, so that's the other way that I can do it. Okay, so now when we talked about regular shear, we determined that we did not have to consider the shear force, the factored shear force within D of the support. That is not the case for this calculation for fracture shear. So for fracture shear, I have to use the VF at the support. So instead of using this this value over here, I wouldn't do that. I would use this value up here, the full shear strength, the full applied shear value. That's what I'm going to check against my notch shear strength. Just going to make a note of that. So I can only use that shear at D away from the support when I'm comparing to VR. But for this calculation, FR, the fracture shear, I need to use the full strength. Now, there is one additional wrinkle, and this is basically a bonus that I can use to squeeze a little bit more shear strength out of my member, and that is taking into account the required bearing length. Okay, so basically there's a part of the clause for the notch shear strength, for the notch shear strength, that says that instead of using the actual full length of the support to calculate E, I could consider what would be the length of the support if I only had to satisfy the actual load there for bearing. What would be the length of the support that I would need, like absolutely need, and then calculate E on that basis. Now this definitely calls for a drawing. So let's recall the way that we actually usually do this. Okay, so this is the way that we have just been taught to do this previously. So we're trying to calculate E for the purposes of calculating our notch factor Kn, for the purposes of calculating our notch strength Fr. Okay, so we want to calculate E, and remember E was defined as being from the center of bearing to the reentrant corner. So here I've shown a drawing of what that situation might look like. I have a beam or a joist sitting on, for example, a light frame shear wall or something like that. And I have my actual bearing length is 140, for example. So let's say it was like a 2x6 wall. And so I'm going to find the center of that wall and calculate my notch length from the center of that wall to the reentrant corner. So that's an easy way. But let's say, you know, like usually my bearing is going to be longer than it has to be, because it's not usually the bearing strength necessarily that's going to govern the design of the beam. You know, the beam might be sitting on a column, and the column has to be a certain size in order for the column to be adequate. So the beam, of course, is going to sit on top of the column. But then, but I might not need that entire column's cross-sectional area to sit on in order for the bearing strength of the beam to be satisfied. So, you know, probably I don't need that full size of the column, but I'm going to put obviously the beam on top of the entire column anyways. So I have a lot of cases where the bearing length is much longer than it has to be, not because it's a poor design or anything, just because there are other requirements that have determined what the size of that bearing surface should be. So recall that this is the bearing strength for effective all applied loads. This is the bearing strength calculation. So if I were to do this in many cases, and I do this calculation to find QR, I'll probably find that QR is much higher than the VF that's being applied at that location. Like then what's the total, or I should say more accurately, the QF, what is the maximum load at the bearing surface? So usually my QR might be way greater than I need. So then what I can do instead is reverse this equation and say this is what the load actually is, QF, and what would be the area of bearing surface that I would actually require in order to resist the beam. Okay, so if I go through that process and I come up with a required bearing area that I would need to satisfy the actual load that's there, then this area is going to be smaller than the actual bearing area that I'm using, because I'm using it because of geometric considerations. And I can figure out a required bearing length, LB required, which is just my bearing area divided by the width of the bearing surface. So what the standard says is that then I can use that actual bearing length and consider that the entire beam is sitting on that actual bearing length, which means that I'm going to be able to reduce my E. And that looks something like this. Okay, so this is my same situation blown up a little bit. Now let's say that I determine that my actual bearing length is something, or that, sorry, my required bearing length is something like this, based on that calculation using QF and QR. Okay, so that means, you know, to get the best result, I'm going to shove that entire bearing surface right up against the near end of the beam, like towards the loading surface of the beam. So I'm going to say that this is my actual bearing area then. I mean, the crosshatch is not the area. The area is obviously on the flat, but that is the part of my bearing surface that is actually required in order to support the load of that beam. So then what I can do is I can find the middle of that bearing area, that bearing surface, sorry, I would say, and calculate E based on that instead of going from the center of the actual support. So you can see how now that I've bunched things up towards that side and I have a shorter bearing surface, then my E is also going to decrease relative to this case up here, where we were looking at the center of the bearing, the center of the full bearing to the reentrant corner. So this is my E required. And so this is a new smaller E. And this here is my new center of support. So this has allowed me to increase my shear strength. So this is a trick that I can use to increase my shear strength. Now, if I do my initial calculation using the center of the actual bearing length and I find that it's fine, then I would have no reason to go through this trouble in order to calculate what is my actual required bearing length and then calculate a new E and then go through, calculate a new KN and calculate a new FR. But for cases where I might be on the edge or I'm trying to squeeze a little bit more strength out of my member, especially because I've had to cut a notch in it, which reduces my strength a lot, then this is a trick that I can use to increase the strength. Okay, so now we've gone over longitudinal shear strength for lumber. We've gone through notch shear, fracture notch strength, fracture shear strength for lumber. And now I just want to sum everything up because there's a few things that we have to consider. Okay, so I have drawn out a summary of all of the different conditions that I have for shear in lumber. And I've drawn at the top an example of a shear force diagram going from VF, my total shear at the support, to VF star, which is the total shear at a location D from the support. And I've identified some sections 1, 2, 3, and 4, 1 being at the center of the support, 2 being at the face of the support, the interior face of the support, 3 being at D from the support, and 4 being at some location where I have my gross area instead of my net area. So I'm going to call this I'm going to identify that this is the location where I have my gross area, and 2 is the location at the face of the support where I have my net area for design. And when I am doing my design, I have 2 things that I have to consider. One is my longitudinal shear, VR, and I have my fracture shear, FR. And I'm just going to kind of briefly summarize what I do for each of these as a guide. So for longitudinal shear, we are going to use the net area, which is at section 2 when I am doing it for lumber. We'll find that when we do it for glulam, we don't use net area, we actually use gross area. And I'm going to check VR, my total shear strength, longitudinal shear strength, against VF at D from the support. Okay, so that's VF star shown at location 3. Okay, so I'm going to use the net area at 2. So I'm going to use this, and I'm going to use this shear at D from the support. And that's the 2 parameters basically that I'm going to use for doing regular longitudinal shear strength check for a lumber beam. Now for fracture shear, I'm going to use the gross area. Okay, and that's at 4. So, you know, wherever all my notches are finished, and I'll cut out. So at that location 4, that's my gross area. And why? Because KN is going to take into account the notch geometry. And I'm going to check this FR, the fracture shear strength, against QF. Okay, and sometimes that's also the same as VF at the support. Okay, QF is not always the same as VF, right? Because VF is the shear. QF is actually the load being applied at that location. But actually, I'm going to use the shear value when I do my check, which is VF at shown at 1. Okay, so I'm going to use the VF that's at the center of the support, this one right here. Okay, and I'm going to calculate E, my notch length, in one of two ways. So I'm going to check E. I'm going to use E for the equation for Kn either from the actual bearing, the center of the actual bearing, or from the center of a required bearing length, which I can calculate using the QR equation. All right, so that's basically it. Those are all of the things you need to do to calculate shear resistance. If you don't have a notch, then you don't have to calculate fracture shear, obviously. All you're going to calculate is the longitudinal shear. Then you're going to use net area and VF at D to calculate that. In the next video, we're going to look at the quite a bit different shear calculation methods for glulam.